In this module, we discuss how to implement the control systems we've been designing. So far in this course, we've been designing control systems sort of in an idealized setting without consideration of their actual implementation. So in this module, we'll discuss how to do that. In particular, we'll discuss some complicating factors that arise when we implement something in the real world. We will also talk about how to design a controller when we do not have a model, which is different than sort of what we've been espousing this whole semester. And then finally, we'll talk about how to physically implement the control algorithm, either in hardware or software. So far, primarily we've assumed a system that has this sort of form: unity feedback, a control algorithm, a plant. But there are sort of complicating factors in the real world that we need to consider. And we've discussed them some in this course so far, but we'll go ahead and discuss them a little bit more in this module. So one thing that we need to consider is model error. So we've been designing our controller assuming some model of the plant, basing our analysis and design. In reality, there's always going to be some error in our model. Our model will not perfectly match the true physical plant, and so we want to know how to deal with that. We also need to be able to deal with sort of the complexities of our system. For example, a couple of things that we often neglect are the dynamics of the actuator and the dynamics of the sensor. So these sorts of things, they don't react instantaneously. Our controller generates some command or control input, and it's not applied to the plant instantaneously. It needs to be generated by some actuator. And our sensor measures the output, but it too doesn't necessarily react instantaneously. And beyond that, it may introduce error into our measurement of the output. So the error that our control algorithm is acting on may not be the true error. So we'll discuss that. We also have unwanted inputs into our system that can enter in different places and have sort of different frequencies and magnitudes. Examples include disturbances, examples include noise, so we'll discuss them. We've talked about nonlinearities a bit. We'll talk about a specific type of nonlinearity, saturation. Every actuator has some physical limit. Every plant has some physical limit. If your actuator is a DC motor and you're requesting, in essence, a certain amount of torque, at some point the motor will not be able to supply a certain level of torque if the request is large enough. And then we need to discuss how we implement our controllers, either in hardware or more commonly in software. And when we implement it in software, it runs on a digital computer, and so we need to discuss sampling. So the sampling of our sensor, the periodic generation of a new control input. And so these are all sort of complicating factors of implementing a control system in the real world, and we will discuss them in this module. So one thing that we often neglect are actuator and sensor dynamics. And so in general, we can always model the actuator and the sensor. We can model it from first principles. Oftentimes the actuators and sensors tend to be electromechanical systems, so we can apply the sort of techniques that we've learned about mechanical systems, electrical systems, electromagnetism in order to generate the model. We can also use sort of a black box approach, a system identification approach, to fit a model to our sensor or actuator, and then use all of the analysis and design techniques that we've learned. The issue with that is that it tends to make your system more complicated. It tends to make it a higher order system, which is more challenging to deal with. If the dynamics of the sensor and the actuator are fast compared to the plant and the controller dynamics, which oftentimes they are, then we can treat them as static. It's this notion of if the poles are at least 5 times faster, then the dynamic or the transient effect of those components will be negligible, and we will just capture them in terms of their effect on the steady state sort of gain of the system. If that's not the case, or if we need a certain level of fidelity that requires the dynamic to be modeled, then we can always do that. Another approach is to remove the sensor altogether, and instead of measuring the output, we can use a model to estimate that quantity. And we'll talk about this in a little bit more detail here. So let's discuss sensorless control, trying to perform control without a sensor. And so what's the motivation for this? One is that some quantities cannot be measured. For example, the state of charge of a battery. So there is no sensor that can measure the state of charge of the battery. So we have no other choice but to try and estimate it from other things. Another motivation is that if we remove a sensor, it reduces cost. You don't have to buy the sensor. It reduces weight. It reduces complexity. You don't have to have software to interact with it. You don't have to have messages being sent over the CAN, whatever. And it's something that can't break. Sometimes you can also have this sensorless control as an option in case the sensor does break. You can switch to another mode of operation where you use this sensorless approach. One thing that we need to consider is that the estimator still has dynamics. So if we have some quantity that we're trying to estimate, we can't get it perfect instantaneously. You know, if the output changes, it takes some time for us to change our estimate. And so just like the sensor has dynamics, our estimator has dynamics, and we need to consider that. In particular, we need it to be faster than the rest of the system, or faster than the sort of required dynamics of our system. You know, if we're trying to control a certain system to perform with a certain speed, and our estimator is slower than that, then we won't be able to achieve our goals. And so the idea, which we'll reinforce on the next slide, is that we can estimate a quantity, so the states of a model or an output of a system, using a model. And we refer to this as sort of open loop estimation. We then, however, can use measurements to correct that estimate. Either we can use a measurement of a different quantity. So if we're attempting to estimate velocity, maybe we use an acceleration measurement to help correct our velocity measurement. We can also try and estimate a quantity that we happen to be measuring. So perhaps we can actually measure velocity, but we know that that measurement has errors in it. And so we can combine that sensor measurement with an estimate from a model to get an even better estimate. And this optimal balance between the sensor reading and the estimate from the model can be done using a technique known as Kalman filtering, which you may have heard of. So here's a figure sort of representing this concept of estimating a state or estimating an output. We also sometimes refer to these estimators as observers. And so the simplest approach is that we basically run a model in parallel with our actual system. So we have this, let's say, an actual plant. We have a model of the plant. We know the command that we're sending to the plant, and so we also feed that to the model, and we use these equations to get an estimate of the output. So instead of having a sensor to measure the true output, we estimate the output based on this mathematical model. And so this is what we would refer to as sort of an open loop observer, or an open loop estimator. We can then actually use some measurement to correct that estimate. And this is what we would call a closed loop observer, or a closed loop estimator. And so in this case, let's consider that our output is a vector. We have multiple outputs. Let's say velocity and acceleration. And let's say we want to estimate velocity and acceleration. So in one instance, if we're using our estimator to estimate something we don't measure, so let's say we don't actually measure velocity, and so our estimate is the only thing that we have. One thing you can do is you can use something that you do measure. So for example, if we use acceleration, we can use our measurement of acceleration to correct our estimate of the velocity. And in that sense, we use this error to apply a correction to our model, or our estimate. And here we have some estimator gain, observer gain, that we can tune in order to get a certain level of performance, a sort of speed of response in our estimate, overshoot, things like that. And so you can see that there's a real duality between how you do estimation and how we did control. We have a gain that we're trying to design, and we're trying to get some sort of dynamic performance. We can also use this notion of an estimator to fix something that we happen to be measuring. So before I said we could estimate velocity because we're not actually measuring that output. We can measure acceleration, but we still want to estimate the acceleration because this acceleration measurement has noise on it, it has a bias in it, different types of errors. And so we can use our sensor measurement alongside a model, an estimate of the acceleration, and combine the two to get an improved estimate. And what we referred to on the other slide is that we can think of this almost as a filter. So we have a measurement, but we are trying to filter it, improve the measurement using this notion of an estimator. So that's why a Kalman filter is called a filter. So in an instance where we don't use sensorless control, or we can't ignore the dynamics of the sensor and the actuator, then we have sort of extra complexity in our system. We have a higher order model that we must consider. And one way that we've discussed dealing with complex systems or higher order systems is trying to decouple the system based on speed. And so the example that we used previously was our motor control system, where we had a torque loop, a fast torque loop that was based on the fast dynamics of the electronics in the motor, and then a slower outer loop that was a speed loop that was based on the mechanical dynamics of the motor. And so we can do that sort of approach again, in particular when we have multiple subsystems working together.